I'm Ms. Ng here, and today I'll be starting the topic carboxylic acids and derivatives. Okay, this will be my first lecture for the topic, and so please get yourself ready with the notes. Okay, so before I begin, all right, let's talk about sweat. Okay, I'm sure we all have this experience of sweating, and then after that we feel like, there's a weird smell, all right, after we sweat. Sweat itself actually is odorless by nature, but the bacteria which covers the surface of the skin will break down sweat. And as a result of this interaction, right, they produce acid compounds that produce distinctive smells, which is why, all right, when we sweat, right, sometimes we don't smell so nice. Okay, so the two common acid compounds associated with odor actually are propanoic acid and 3-methyl-butanoic acid. As you can see, propanoic acid has a sour smell, and 3-methyl-butanoic acid has a chili smell. So maybe that explains why we don't smell so good after sweating. Okay, we'll come more to talking about these carboxylic acids in a while, but this is just an introduction, all right, to where we can find carboxylic acids in our life. Okay, and also, all right, certain medications, especially this dinoproston, all right, is a type of prostaglandin. Okay, and also see the carboxylic acid group here with COOH group. Okay, it's also used for labor and medical purposes. So there's several uses of carboxylic acids. Okay, so let's begin. Now, for carboxylic acids, all right, this is the structure of carboxylic acids. I think by now you will have recognized that, all right, there is a carbonyl group. You can identify C-O, carbonyl, and OH hydroxyl group. But when they come together, they form COOH group, all right? We call that carboxyl. Okay, it's kind of like a combination between carbonyl and hydroxyl, therefore carboxyl functional group. However, all right, when these carbonyl group and hydroxyl come together to form carboxyl group, all right, they do not really react like carbonyl compounds or alcohols. So later we'll also take a look at what reactions carboxylic acids will undergo. Okay, and just to highlight, the carbon in the COOH group is sp2 hybridized. As such, right, the shape will be trigonal planar around this carbon, and the bond angle will be 120 degrees. Now, this hybridization, all right, is not new. The shape and bond angle is also not new as well. Okay, so just a quick recap. Okay, as for the content we'll cover for these carboxylic acids, okay, you can see that they are quite simple, and you may be glad to hear that there will not be any mechanism that you need to learn for this topic, this chapter as well. So these are the first 5 points will be what I'll be covering for today's session. All right, and the next session, we'll move on to carboxylic acid derivatives. Okay, so for nomenclature, all right, we will replace the E of the corresponding alkene with oic acid. Okay, and remember that the carbon in the COOH group will be the carbon number 1. Carbon in the COOH group will be carbon number 1. So let's take a look at a few examples. All right, the first example only got 1 carbon. Okay, so if there's only 1 carbon in the alkane, it'll be methane. So this is a carboxylic acid, it will be methanoic acid. All right, next example, there are 2 carbons. If it is an alkene with 2 carbon atoms, we call it ethane. So a carboxylic acid with 2 carbon atoms, we will call it ethanoic acid. All right, so you see how the E is replaced with the oic acid. Okay, now this is a COH directly bonded to the benzene ring. We call it benzoic acid. All right, and the last one, all right, also has got 2 carbon. As in the side chain, right? There are 2 carbons. All right, we consider the benzene ring here as a substituent. So it's phenyl ethanoic acid. Okay, phenyl ethanoic acid. Okay, moving on to more examples. Now, as I mentioned earlier, the carbon in the COH group, we consider that as the first carbon. Therefore, if you number it, the 3 carbon atoms in this example, all right, you will see that there is a OH group on the second carbon. Therefore, all right, we call it 2-hydroxyl propanoic acid. Propanoic acid, okay, is because there are 3 carbon in the carbon chain. Okay, and if there are 2 carboxylic acid groups in this case, all right, we call it dioic acid. And in this case, 2 carbons, ethane dioic acid. Okay, and the last one, all right, is benzene 1,4-dicarboxylic acid. Okay, when it comes to a benzene ring, we identify what is the position on the benzene ring with the COOH group. Hence, benzene 1,4-dicarboxylic acid. Okay, it's a bit different from the dioic acid. Okay, so please take note of that. All right. Okay, so the sorts of carboxylic acids, all right, we will also come into more details later. All right, we'll replace the iic acid with ATE. So for example, I have propanoic acid, the salt, the anion, all right, we call it propanoate. Okay, CH3, CH2CO minus propanoate. And if it's CH3, CH2CO minus Na plus, we call it sodium propanoate. Okay, so that is how, all right, the sorts of carboxylic acids are named. Please take note of that as well. And with that, we will do checkpoint number 1. All right, you can see that there are 4 compounds that will like you to draw the displayed formula. Okay, so can I give you 1 minute to draw it out? Okay, displayed formula, what does that mean? And your time begins. Okay, actually 1 minute's up. I hope you have had the chance to draw all the displayed formulae. Okay, so a reminder, displayed formulae, all right, all bonds must be drawn out. Okay, show all the bonds, yeah. First one, part A, 2-chlorobutanoic acid. Butanoic acid has got 4 carbons, all right. So on carbon number 2, there's a chlorine, okay. So just to show you, all right, carbon number 1 starts from the carbon on COOH group. Therefore, all right, this will be how I number the carbon atoms. Okay, take note that because earlier I mentioned the carbon, all right, in the COH group is sp2 hybridized, you should show the trigonal planar shape around C, and actually around OH, you'll see later that usually we try to draw it and show it as a band, all right, shape as well, all right, because of the number of bond pair, lone pairs around it. Okay, trichloroethanoic acid. So ethanoic acid, 2 carbons, all right, trichloro, there are 3 Cl substituents on the second carbon. Again, make sure you show all the bonds. A lot of times students forget to show all the bonds for COOH group, or sometimes they draw the C double bond O, but they did not show the bond between O and H. So please be careful and pay attention. 2-hydroxyl hydroxyl benzoic acid. So maybe we can draw out benzoic acid first. All right. And then on carbon number 2, there's hydroxyl group. Okay, so this is how it looks like. You can see if we draw benzoic acid first, all right, followed by the OH group, it will be probably easier for you as well. And last one, butane dioic acid. All right, there are 4 carbons in butane dioic acid. The 2 carbon at the ends will be part of the COOH group. So that's for drawing, displayed formula, as well as nomenclature of carboxylic acids. Okay, I hope you have taken down the answers if you have not had a chance to attempt it. I will now move on to the second part, physical properties. Okay, so a few physical properties that we'll be looking at for carboxylic acid. First one being boiling point. Now, if we take a look at the COOH group, all right, you will realize that carboxylic acids, all right, they are capable of forming hydrogen bonds between the molecules, all right, because of the COOH portion of the carboxylic acid. Now, recall or recap, hydrogen bond, right, there should be a lone pair on either O, F, or N, as well as a hydrogen bonded to O, F, or N, okay? So if you have to draw the hydrogen bonds between 2 carboxylic acid molecules, reminder, okay, there should be a lone pair on oxygen. There should also be delta plus on H in the OH group, delta minus on the O in the OH group, okay? And then all the partial charges are, please take note as well. And then you will draw a dotted line between H with the delta positive and the lone pair on O and label it as hydrogen bond. Okay, if they ask you to illustrate hydrogen bond between carboxylic acid molecules, this is how you do it. In addition, all right, the R groups will have ID-ID interactions between the molecules. Okay, and when we look at boiling point or compare the boiling point of carboxylic acid, we will actually compare the strength of the ID-ID. So let's take a look at how the ID-ID interaction between the molecules will change. All right, as the number of carbon atoms in the carboxylic acid increases, okay, number of electrons increases, therefore strength of ID-ID interactions between the molecules increases, which requires more energy to overcome these stronger ID-ID interactions, and therefore boiling point increases. Okay, so while we compare the number of carbon atoms in carboxylic acid, all right, when we want to compare boiling point, take note that you must still write down this point, number of electron increases, okay, before you move on to say strength of ID-ID interactions between the molecules increases. All right. So at standard conditions, right, those carboxylic acid with lower number of carbon atoms, they're actually liquids. Okay. And if we move on to look at this table, okay, earlier we compared the boiling points of different carboxylic acids. But if we want to compare carboxylic acids and alcohols boiling points, okay, we also realize that carboxylic acids generally have higher BP, all right, compared to alcohols of similar MR. Why is that so? Right? So I think if you look at these two structures of carboxylic acid versus alcohol, you probably have an idea that it has got to do with the hydrogen bonds that they form, all right, between molecules. So for carboxylic acid, there are 2 reasons, okay, why the boiling point of carboxylic acid is higher. Okay, first reason, there are more sites for formation of hydrogen bonds when it comes to carboxylic acid versus alcohol. Okay, so it leads to more extensive hydrogen bonds formed. Since there are more sites, there are more lone pairs, all right, on the oxygen atoms, etc. Okay, so you can see for yourself these 2 illustrations. Okay, second reason, all right, you can see that this particular HR has got a bigger delta positive as compared to the OH on alcohol. Because of the electron withdrawing C double bond O group, okay, this is what I'm talking about. Because of these electron withdrawing C double bond O group, it makes the OH bond more polar. All right, so which is why I could draw the delta plus on the hydrogen like bigger. All right, in other words, there will be stronger attractive force between the hydrogen of this OH group and the lone pair of electrons on oxygen of another acid molecule. All right, so it leads to stronger hydrogen bonds. So comparing boiling point of carboxylic acid versus alcohol, all right, two main reasons. Carboxylic acids are able to form more extensive hydrogen bonds between molecules and as well as stronger hydrogen bonds between the molecules. Then, of course, you can substantiate further and explain why are there more extensive hydrogen bonds as well as stronger hydrogen bonds. Okay, so 2 points to remember, yeah, and they are boxed up in this slide. And so this is for comparing boiling point of carboxylic acid with alcohols of similar MR. The next physical property we'll look at is solubility. Now, as you can guess by now, right, carboxylic acids are able to form hydrogen bonds with water molecules. And again, if you have to illustrate this, all right, make sure that you have the lone pair on oxygen being bonded to a hydrogen, which is bonded to oxygen. Okay, and all the partial charges should be labeled properly as well. Okay, so lower carboxylic acids are miscible with water because of the ability to form hydrogen bonds with water molecules. Okay, and carboxylic acid can also partially dissociate in water according to this equation. Okay, but take note that there is a non-polar hydrocarbon chain. The non-polar hydrocarbon chain, right, they cannot form favorable interactions with water molecules. So it's only the COOH part of the molecule that can form hydrogen bonds with the water molecules. So when the length of the non-polar hydrocarbon chain increases, all right, the carboxylic acid will be less soluble in water, but become more soluble in non-polar solvents. All right, because the R group, right, they will form favorable interactions with non-polar solvents instead. Okay, so this is for solubility of carboxylic acids. Okay, next one, dimerisation, ability to form dimers. Okay, that means you, how can two carboxylic acid molecules, all right, form a dimer? Now, take note, all right, they will do it through the formation of hydrogen bonds, as you can see illustrated here. I believe in chem bonding last year, we also talked about this before. Right, it occurs in pure carboxylic acids, which means that it will occur when carboxylic acids are in solid, liquid, or vapor phases, as well as in non-polar solvents. So the next question you may ask is then how about in water and aqueous medium? Will they still dimerize? Okay, let's think about it. Earlier when we say carboxylic acid in water, all right, chances are that because water is a solvent, there are many more water molecules compared to acid molecules. So the carboxylic acid molecules will actually form the hydrogen bonds with water molecules instead. All right, the carboxylic acid molecules, when in aqueous medium, they will form the hydrogen bonds with water molecules instead. So they will not dimerize. Okay, so dimerization, when two carboxylic acid molecules form the hydrogen bonds with each other, all right, they form a dimer. Okay, so as you can see, so far we have just been doing more or less a recap on previous concepts. Okay, so the next part, acidity, all right, will be something new, and it is also an important part of this chapter. So please pay very careful attention to what we're going to go through. Okay, Carboxylic acids are weak acids that dissociate partially in water. Earlier I mentioned. So in water, all right, if, they will form RCO minus. We call it the carboxylate anion. Okay, so when we say that they are weak acids, all right, however, they are still considered stronger acids than like alkane, alkenes, alcohol. But weak acid is because in comparison to HCl, H2SO4, all right, carboxylic acids are definitely weaker acids. But now we take a look at comparing the acid strength with other organic compounds. How can we compare the acidity of carboxylic acids then? Okay, I want to recap the acidity concept that we learned from hydroxyl compounds a few lectures ago. Now, when we talk about acidity of alcohol and phenol, all right, we will look at the stability of the anion. All right, and if you recall, the more stable the anion, all right, the position of equilibrium will lie more to the right, and therefore the acid will be a stronger acid. So we will apply a similar concept to carboxylic acid. All right, we look at the stability of the carboxylate anion, the RCOO minus. Okay, so the carboxylate anion, RCOO minus anion, is actually stabilized by resonance. So what do we mean by that? Okay, you can see these diagram in your notes as well. All right, these are actually the two equivalent resonance structure. As you can see, because of the overlapping of the p orbitals in the CO minus, right, we see that the negative charge is delocalized over the COO minus group. Okay, delocalized, to put it simply, all right, it's like the negative charge can be spread out over the COO minus group. Okay, but we don't use the word spread out when we are like explaining in our tutorials, tests, and exams. Okay, we use the word delocalized, but I just want to sort of like explain using simpler terms what is the meaning of delocalization of negative charge. Okay, so this is probably easier to understand representation. Okay, the minus charge is not like on any specific oxygen, but rather spread out over the COO minus group. So you can see that there is a factor stabilizing this anion, which is why comparing to alcohol phenols, all right, these stabilization by resonance will cause the carboxylic acid to be a stronger acid as compared to alcohols and phenols. All right, so when they ask you to compare alcohol and phenol, this is the reason we will give. Okay, the next part we'll continue to discuss acidity, but we will be comparing the acidity of different carboxylic acids. All right, so this is not in your notes, but I just want you to think like, if you have these two different carboxylic acids, make a guess. Okay, which one do you think is going to be a stronger acid? So recap, to determine which one is a stronger acid, we look at the stability of the carboxylate anion. So are there any factors that will stabilize or destabilize any of the carboxylate anion? Okay, think about it first, later we'll go through and then we'll come back to this. Okay, so as mentioned, we look at the stability of the carboxylate anion. So if, all right, we have an electron donating group, all right, attached to COO minus in this case, like an alkyl group, what the electron donating group will do is that, because it's electron donating in nature, it will intensify this negative charge. All right, when it intensifies the negative charge, right, essentially it's donating electron density to the COO minus group. All right, it's the electron donating group. Of course, it will donate electron density to the COO minus group. And as a result, the negative charge, they cannot spread out. All right, so we say that this intensifies the negative charge. So do you think when negative charge is intensified, will it stabilize or destabilize the carboxylate anion? of course, it will destabilize the anion. And when anion is less stable, destabilized in this case, all right, the acid will be weaker. So what if I have an electron withdrawing group instead of electron donating group? So earlier we see all the fluorine atoms, right? Make a guess, are they electron donating or electron withdrawing? Okay, so if you have electron withdrawing group, all right, the reverse will be true. Okay, because of the electron withdrawing group, it can disperse the negative charge. Okay, I use the word spread out here again to make you understand what's the idea of disperse negative charge, but we don't use this term, all right, in our answers. Okay, it's just for understanding. All right, because of the dispersal of the negative charge, it will stabilize the anion, and therefore the acid will be stronger. Okay, so when comparing the relative acidity of carboxylic acid, we don't have to talk about like stabilized by resonance, etc., because the stabilization by resonance occurs in all the carboxylic acid. So we'll look at whether the CO minus is bonded to an electron donating or electron withdrawing group. All right. So if we go back to the earlier two examples I showed you, which do you think is the stronger acid? Okay, I think a very obvious difference is really between this CH3 group here and CF3 group. So fluorine is a very electronegative atom, yeah? So which one do you think is the stronger acid? How do we compare the groups attached to the COH or the CO minus as we compare the stability of the carboxylate anion? Okay, so alkyl group is electron donating. Earlier we mentioned that as well. It will intensify the negative charge on the carboxylate anion. All right, destabilize the anion, and therefore it will be a weaker acid. On the other hand, I have fluorine, all right, electron withdrawing group over here. It will disperse the negative charge, stabilize the anion, and as a result, this CF3COH will become a stronger acid. All right, so we always ask ourselves three questions. All right, negative charge, is it intensified or is it dispersed? Anion, is it destabilized or stabilized? Lastly, as we conclude, is the acid going to be stronger or weaker? So these 3 points are always the main points that you should have in your answers when comparing relative acidity of carboxylic acids. Okay. Now, we also have got benzoic acid over here. Okay. Sorry. This should be a circle in the middle. Yeah, circle in the middle. So benzoic acid is stronger than aliphatic acids. Why is that so? Okay, let's take a look at the benzoic anion. Okay, maybe I draw it out properly. This is the benzoic anion. You can see that the carbon atom of CO minus is sp2 hybridized. All right, and the benzene ring, right? The carbon atoms are also all sp2 hybridized. Therefore, all right, the negative charge can delocalize into the benzene ring due to the overlapping of the p orbitals. All right, this is also known as delocalization. So when that happens, the negative charge is delocalized in the benzene ring. Of course, okay, it will stabilize the anion as compared to aliphatic carboxylate anion. As a result, benzoic acids are stronger than aliphatic acids. Okay, because of the overlapping of the p orbitals, the negative charge can delocalize into the benzene ring and make the benzoic anion more stable or stabilize the benzoic anion, making benzoic acid a stronger acid. Okay, so, but this only happens when the COH is directly bonded to the benzene ring, okay? Then we can use this factor to explain. So in this context, delocalization happens when the negative charge is spread out over more than one atom due to overlapping of orbitals. So we mentioned negative charge delocalized into a benzene ring due to the overlapping of the orbitals. Okay, then when we say dispersed negative charge is usually, all right, the negative charge is spread out due to the attractive force of an electron donating group. So take note of the difference because we use dispersal of negative charge as well as delocalization of negative charge earlier. There is a slight difference depending on how the negative charge is spread out. Okay, and with that, we come to checkpoint 2. All right, now we are going to look at the following carboxylic acid and arrange them in order of increasing acid strength. Okay, so what will we be thinking about? All right, 3 minutes to attempt first on your own. And 3 minutes is up. Let's take a look at how we are going to write the explanation for this question. Okay, part A, we are comparing all the carboxylic acids as stated here, and I think it's very evident that the difference lies in the halogens. Okay, so under the explanation part, all right, the few bullet points is to guide you on what you should be looking out for. And the rest of the lines is for the explanation. So firstly, we will look at the electronegativity differences. So you will be able to tell that electronegativity increases from I to Br to Cl to F. So usually when we say increases from something to something, we can also make use of this in bigger less than sign. Okay, it may be easier when you put it in like that. All right, so we know definitely F is the most electronegative from the way you write. As a result, let's look first electron withdrawing or electron donating effect. So in this case, it's electron withdrawing effect, and it increases from iodine to bromine to chlorine to fluorine. Okay, so of course, as the electron withdrawing effect increases, all right, the negative charge will be dispersed more effectively with a more electron withdrawing group. Okay, so the stability of the anion will increase from CH2I CO minus all the way to CH2F CO minus. Take note, when we compare, we always compare the stability of the anion. Then we conclude, all right, which is a stronger acid. Okay, so of course, the more stable the anion, the stronger the acid. Okay, so these are the points that we should consider or at least go through in our head. Now, then when it comes to writing the explanation, okay, it's going to be quite wordy, but you can try writing on your own first and then comparing it later, all right? But let me show you first. Okay, so similar to what we mentioned, all right, we just put it in explanation this way, all right? Compare electronegativity and electron withdrawing effect. Then F, being the most electronegative, is the most electron withdrawing. Therefore, it will disperse the negative charge on the COO minus group most effectively. Okay, that's the word we use. Disperse the negative charge on the COO minus group most effectively. Then we conclude the stability of the anion before we say that 2-fluoroethanoic acid is the most acidic. Okay. So this is actually how we will write the answers. Okay, you can review this later after you try writing it on your own with the earlier points mentioned. So for part B, okay, part B, the electron withdrawing group, all right, it's actually the same Cl. So the difference, where lies the difference then? The difference is that for CH3, CHCl, COH, all right, the first carboxylic acid, the carbon, sorry, not carbon, the electronegative Cl atom is closer to the COO minus group. Okay, so the difference is the proximity of Cl to the CO minus group. Okay, so it will exert a stronger electron withdrawing effect. As a result, same phrasing as before, the negative charge on the CO minus group is dispersed more effectively, and stability of anion, all right, will be it will be more stable, CH3, CHCl, CO minus as compared to CH2, Cl, CH2, COO minus. Okay, so from there you can conclude the acid strength. The 2-chloropropanoic acid is more acidic than 3-chloroethanoic acid. Okay, so that is the difference. 2-chloro versus 3-chloro. So if you're going to write it out in prose, everything, okay, so we will say that electron withdrawing Cl group is closer to the CO minus group for 2-chloropropanoic acid, disperses the negative charge more effectively in the anion, as then which anion is more stable than which anion. Write out the anion. You don't have to name it, but you can just write out what the anion is. Okay. As a result, 2-chloropropanoic acid is more acidic than 3-chloroethanoic acid. Okay. So this is how the explanation would be. So you can see that in this example, 2A and 2B, we had to explain, all right, the different electron withdrawing strength, okay, which is a stronger electron withdrawing group, which is a weaker one, as well as the proximity of the electron withdrawing group to the CO minus group. Okay, so these are the effects of these two factors. All right. Okay, so to summarize the acid strength of carboxylic acid in relation to others, all right, definitely mineral acids like HCl, they are stronger than your carboxylic acid, but carboxylic acid is considered stronger than phenols and alcohols. All right, so all of them will react with reactive metals. All right, mineral acid, carboxylic acid, and phenol will react with NaOH. And carboxylic acid and mineral acids will react with carbonates and hydrogen carbonates. Phenol and alcohols will not. All right, don't worry, we will talk about these reactions later on, all right, or the next lecture. So just bear this in mind first, all right? The acid strength, all right, will also affect their reaction, okay, with metals, NaOH, and carbonates. Okay, moving on to preparation of carboxylic acid, yeah? Okay, if you look at your notes, you can see that there are two categories, either by oxidation or by hydrolysis. Now honestly, most of these reactions I'm going to talk about later are recap of previous chapters, all right? So I will not elaborate more, okay? First one, by oxidation, we can oxidize primary alcohol and aldehydes, okay, to carboxylic acids. So please fill in the blanks in your lecture notes. All right, so we will, in order to balance this equation, right, we will usually write out the products first. So from CH3, CH2, CH2OH, propane 1-ol it will get oxidized to propanoic acid. All right, we will balance the hydrogen and then oxygen usually. Okay, so you get this equation. The next one, all right, will be, what's the product? The product you will get is this carboxylic acid here. And can I just ask, like, what if KMNO4 is used? Okay, what is KMNO4 is used for this particular aldehyde? Okay, the next slide will review the answer. All right, if KMNO4 is used, all right, the whole side chain actually get oxidized, right? So side chain oxidation of alkyl benzenes can also result in carboxylic acids. So if we use KMNO4 for methylbenzene as well as this aldehyde, okay, it will give you benzoic acid. Okay, but the second equation will have CO2, yeah, because this other carbon will become CO2 in the oxidation. Okay, so balance it properly. And the next one, all right, you could also probably recall in carbonyl compounds, we also learned aryl ketone can be oxidized by KMNO4 to give you benzoic acid in this case. All right, you may want to add that down as well for aryl ketones. Okay, and the last oxidation way to prepare carboxylic acid will be oxidizing alkene, all right, with this particular structure over here. So the CC double will break and you will get benzoic acid. And of course, in this case, CH3COH. All right, so you get two carboxylic acids with structure RCH, double bond to CHR prime. Okay. So with that, we have finished up the part on how to prepare carboxylic acid using oxidation. We can oxidize primary alcohol and aldehyde, alkyl benzenes, as well as certain alkenes to give you carboxylic acids. The next way to prepare carboxylic acids will be by hydrolysis. So we have we have hydrolysis of nitriles, all right, C triple bond N nitrile group. Okay, so under acid hydrolysis, if you use like dilute HCl, heat under reflux, you can convert the CN group to COOH. All right, and we can also use alkaline hydrolysis. So NaOH equals heat under reflux. We will get the carboxylic acid salt first. All right. Sorry, the carboxylate salt, carboxylate anion. All right. RCO minus, but you can also convert it to RCOH easily by adding in an acid. All right. So for the examples on page 10, the rest of the examples on page 10, I think it's quite easy to come up with the product. So first equation, acid hydrolysis. All right, we'll get the carboxylic acid. And the second one is alkaline, all right, hydrolysis. We'll get the salt. Okay, so we'll leave it as the salt because there's no further mention of like adding with acid. So you have it remain as CO minus, alkaline hydrolysis. Okay, so from page 8 to 10, honestly, these reactions are not new. So it's more of a revision for you guys. Okay. And the last part, hydrolysis of acyl chlorides and ester, not to worry. We will cover later in that chapter. All right. So I'll talk more about it when the time comes. Okay, so we'll break the CCl bond in acyl chloride to give the carboxylic acids, as well as the C single bond O in esters to get the carboxylic acid. Okay, this is in short what's going to happen. And the last part for today's lecture will be reactions of carboxylic acids. Now, carboxylic acids, that because of the close proximity of the C double bond O group and the OH group, the carboxylic acids do not behave exactly like carbonyl compounds or alcohols. Okay, so for example, carboxylic acids do not undergo nucleophilic additions, all right, unlike carbonyl. Okay, so it differs from carbonyl compound in the sense that it does not undergo nucleophilic addition. And it also won't undergo condensation with 2,4-DMPH. However, okay, carboxylic acids, because of the electron deficient carbon, it can still be attacked by nucleophile. But carboxylic acids are less susceptible towards attack by nucleophile, which means that they are less reactive towards nucleophile, but they can still react. Okay, they are less reactive towards nucleophile. And the lone pair on oxygen, as you can see over here, the lone pair can delocalize into the pi bond of the C double bond O. Okay, you can see the overlapping of the p orbitals. So the lone pair can delocalize into the C double bond O pi bond. All right, so there is a drift of electron density to the carboxyl carbon. So the carbon is not so electron deficient. All right, the delta plus is not so big. All right, it will reduce the delta plus on carbon, which is why carboxylic acids are generally less susceptible to attack by nucleophile. Okay, so let's take a look at what are the reactions they can go through then. Okay, the C single bond O can break. All right, so the OH group can be replaced. This is known as nucleophilic substitution. All right, or if you want to be more precise, nucleophilic acyl substitution. So this is different from the SN1 and SN2. Do not confuse with that. All right, because this is for carboxylic acid nucleophilic acyl substitution. The OH bond can also break. So when there's an OH bond breaks, there's a loss of H plus. So this is when we look at the acidic property of carboxylic acids.
We'll now take a look at the typical reactions of carboxylic acid. So the first type of reactions we are looking at will be those involving the cleavage of the OH bond. This is due to the fact that RCOH, alright, is an acid. So it will take part in acid-metal reactions as well as acid-base reactions. So first, let's take a look at acid-metal reactions.
This is pretty similar to what we have talked about for phenol and alcohols reacting with reactive metals. The type of reaction is acid-metal reaction. All right. So if I have a carboxylic acid and a reactive metal, okay, I'll form a salt. Okay, in this case, all right, it will be CH3COO minus bracket 2, Mg2 plus, magnesium ethanoate. All right, CH3COO minus is an ethanoate ion. Okay, so please remember to balance CH3COH as well. And of course, H2 gas will be released in acid-metal reactions. Okay, so I don't think this is new since we've talked about similar reactions, similar acid-metal reactions for the previous chapters. Next, we have reaction with bases.
Now let's take a look at how this acid-base reaction can take place.
Carboxylic acids will also react with NaOH, right, to give you the salt and water. So for this example, given here's calcium hydroxide and ethanoic acid, all right, we'll form the salt calcium ethanoate. Take note, all right, of the formula, of calcium ethanoate. And balance the equation. Okay, water will also be formed in this case. And the last one for reactions involving the breaking of the OH bond, okay, will be acid carbonate. Okay, but before that, take note that for acid-base reaction now, we need to have aqueous medium because carboxylic acids can only show their acidic property in aqueous medium. All right, so this is the reason. Carboxylic acids can only show their acidic property in aqueous medium.
Carboxylic acid can also react with carbonate or hydrogen carbonate. This type of reaction is known as acid-base reaction. Please make the correction in your lecture notes as we would identify this type of reaction as acid-base reaction and not acid-carbonate reaction. Okay, so take note, if we ask the type of reaction for carboxylic acid and carbonate or hydrogen carbonate, you should be writing it as acid-base reaction. Now, you can see from this equation, carboxylic acid and, for example, in this case, sodium carbonate will give you a salt, CO2 and H2O. Similarly, it can also react with a sodium hydrogen carbonate to give you salt, CO2 and H2O. And this type of reaction can actually be a distinguishing test for carboxylic acid due to the evolution of CO2. And we can test for the evolution of the CO2 gas with lime water because CO2 will give you a white PVP with lime water. Phenols and alcohols, if you recall from previous lectures, they do not react with carbonate and hydrogen carbonate. So for those reactions, there will not be any CO2 evolved, whereas for carboxylic acid reacting with carbonate or hydrogen carbonate, there will be CO2 gas evolved and we can test for the evolution of the CO2 gas. The carboxylate salt in this case, alright, your RCO minus Na plus can react with stronger mineral acids, okay, and it will accept the H plus from the stronger mineral acids such as the HCl to give you the carboxylic acid. Okay, so this is for reaction of carboxylic acid with carbonate or hydrogen carbonate.
Okay, this is a summary to show how alcohols, phenol, and carboxylic acid react with metal, base, and carbonates or hydrogen carbonates. Okay, so this is what I've elaborated before. So I hope, all right, this chart or this table here will help you to remember better. All right. And with that, I've come to the end of today's lecture. All right. And these are actually, all right, the first 5 bullet points are the things that I've gone through today. I'll continue though with reactions of carboxylic acids in my next lecture and also talk about carboxylic acid derivatives. Okay, so thank you very much for your attention. I will end the meeting for all.